So, advection is drift, often from the bulk motion of ambient material. So this means, like, if you're looking at a process that takes place in air, you might have wind moving the body of air to the side, or if you're looking at a process that takes place in water, you might have some current that's moving the environment in which the system is taking place is being moved along. So the idea for advection is that flux is proportional to density. And so that means for us then that flux is equal to some constant times the density of the thing that we're interested in. So if we have that the source term is identically zero in our conservation law, the conservation law is going to look like u sub t plus, and then our phi of x is going to be cux, and then with f equal to 0, this will be equal to 0 right here. And so this is referred to as the advection equation, or sometimes a transport equation. This kind of drift is referred to as transport. Sometimes the term convection is used, whatever. So let's see. So now the solutions of an equation like this are given in terms of some continuous function g. So this notation, if you're unfamiliar with it, just means that g is a function of a single real variable, and its output is a single real variable. So in other words, it's just a standard function from r to r, one number in, one number out. So if g is a continuous function, actually, you know what? Sorry, we need a derivative here. So if g is a differentiable function. Okay, if g is a differentiable function, then the solution to this equation is given by g of x minus ct. So that's a solution for us. And so just to check real quick, if we have this formula for u and we take its time derivative, then we get minus c g prime, and I can use the prime because g is a function of a single variable, so it's just the derivative with respect to that one single variable. It's not ambiguous. And on the other hand, we have the partial with respect to x of u, and that's going to be g prime x minus ct. So if we multiplied the partial derivative with respect to x times some number c and add it to u sub t, you can see those things are going to cancel. Great. So let's see. So that verifies that it's a solution. So now let's take a look at this solution. And if we look at some time snapshots, so u at x0, this is just going to look like g of x. So what that's telling you right there is that g is the initial conditions. If we look at what's happening at t equals 1, then we have g translated to the right by c. If we look at u of x at time 2, then we have g is x translated to the right by 2c, and so on. So this is, so we've got, let me just say, we've got this is shifted by c, and then this one is shifted by 2c. So what that's telling us is that if we have a graph for g that looks like maybe this, something like that. Okay, so there's g. Then if I look at a future moment in time, so then maybe something like this. That's going to be, and then, actually here, let me move the label over there, like that, okay. And then at some other time later on, we'll have something that looks like this one over here. Whoops. Oh, stop. And so on and so forth. So you can see that it is a rightward traveling wave that's moving at speed c. Okay. And so if we graph this as a 3D surface, we'll have something that looks like this. So the key point to notice here is that time is moving in this direction right here, and the wave is moving that way. So it's moving at a slant, and that's given by the speed c. Another thing that I want you to notice is that if you look at, say, the crest of the wave, it's traveling along to the right also at speed c. And we can see that there are these curves. So if we look along these curves here that have this particular angle, the function has a constant value along those particular curves.